Okay, so for now, we will have module 7 and 8, and these are hypothesis testing. So I'll be presenting you a PowerPoint presentation. Credits to the owner, Sir Merino Bantasan. He was the one who have given me a copy of this presentation. So for the hypothesis testing, okay, let's start. Right? Before that, let us review first some concepts in statistics. Again, when we talk about population, the whole of this is what we call population. And a part of it is called sample. Again, the whole of this is what we call population, and part of it is sample. Now, these are symbols, okay? For the sample mean, the symbol is X bar, right? And for the population, that is mu. Of course, for the proportion also, which we did not yet discuss, the proportion is P, what do you call it? P hat, okay? The P hat is for the sample. Okay, so we have the population mean. When we talk about population mean, and the population proportion. The proportion, we did not yet discuss this, but when we talk about population mean, it's the mean from the population. Again, any value coming from the population, do not forget this, parameter. I'm sorry, let's repeat. Okay. When we have data from population, that is parameter. Any data from the sample is called statistic. Okay. So PP. That is your clue when we talk about, when again, any data from the population is called parameter. Any data coming from the sample is called statistic. Okay. Now, let's go to the definition of terms. Again, you have to make sure that you understand the definition of terms, because that will be a foundation of our topic, our lesson. So hypothesis testing. So when we say hypothesis testing, it is a statistical procedure in determining which hypothesis is more acceptable as true or which hypothesis is more likely to be false. Okay, isn't it sometimes that during our elementary days, there's this step in scientific procedures that you call formulator hypothesis. When we say hypothesis, these are the probable output of a certain study, and hypothesis testing is the process in which you are going to test that hypothesis if it's true or false. Okay, so that is hypothesis testing. And for the hypothesis, we have a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. Of course, you will state your hypothesis. That is a supposition or proposed explanation. Okay? And that is your feeling. That is your educated guess. That is hypothesis. So maybe your guess is, sometimes if you study the level of competency of senior high school student of UC. Okay, so what is your hypothesis? Their level is above average. That is one of the hypotheses, or it could be below average. So that could be the possible outputs that you can have, right? So that is hypothesis. Now, steps in hypothesis testing or testing hypothesis. So for your hypothesis testing, first is the hypothesis. You have to make first your hypothesis, and we are going to give examples on that later. Okay. Next, we have to make sure that you know the critical value, or the ones what test are you going to use? Are you going to use t-test, z-test, or other tests? Next, test statistic. Okay. After determining the critical value, we are going to choose that test statistic, okay, which is the t-test, z-test. I'm sorry for that. And next, we have decision. Okay, so from the test statistics, from the ones that you have solved already, you are going to decide what you are going to do there. Okay, next is the conclusion. On your on your module, there is steps 5 and 6. Steps 5 and 6 are actually just the same. They're part of the conclusion. That could be already. Okay, next. So we have hypothesis. There are two types of hypothesis. We have null hypothesis, or we call HO, and we have alternative hypothesis, which we call HA. Again, HO for the null hypothesis and HA for the alternative hypothesis. And for each of the type, there is this. For the alternative hypothesis, we have non-directional and we have directional. What do we mean by non-directional and directional? Okay. For our null hypothesis, it is always that we use equal for the null hypothesis. And for the non-directional alternative hypothesis, we use not equal to. And for the directional, we have greater than or lesser than. From the word itself, from the alternative hypothesis, when we talk about non-directional, meaning the hypothesis doesn't have any direction. So if this is the normal curve, when we talk about non-directional, we are talking about this, both of this. Okay? But when we talk about lesser than or greater than, that is directional, because it will tell you that when it's lesser than, then it's here. But if it's greater than, then it's here. So lesser than, greater than. So that's why it is directional. So it tells you where is the direction of your data, or what part are you going to accept or reject. That's why it's called non-directional and directional. Okay. Later, I will give you examples on directional and non-directional. Okay, next. Okay, let's have an example. So, example number 1. Our HO, or our null hypothesis, the average score of all students, completers of UC is in the National Achievement Test is 57. So, simply, what is the answer there? Can we just translate it into mathematical form? We have mu is equal to 57, meaning the mean is equal to 57. That is your HO. Okay, now we have the alternative hypothesis. The average score of all students completers of UC in the National Achievement Test is not 57. So it's not 57. So when we say is not, that means that we are going to use not equal to 57. Now, is that directional or non-directional? And if we talk about this, it is non-directional. Right? It's non-directional because we have used not equal to. But here, there is another alternative hypothesis. What if our alternative hypothesis is this one? The average score of all student completers of UC in the National Achievement Test is higher than 57. So which means that mu is higher than 57. It is directional. Because it's telling you that if there is the normal curve, you're talking about values here on the right side. That's why it is directional. Okay, next. Okay, let's have an example. An instructor feels that using a module will enhance the performance of his students in statistics. In the past, the average grade of students was 75. So let us formulate our null hypothesis. So what will be your null hypothesis? Our null hypothesis is the average grade of students in statistics is equal to 75. Now, for our alternative hypothesis, what could it be? It is the average grade of the students in statistics is greater than 75. Okay, why is it that we use greater than there, but you do not see any greater than in the problem? If you are going to analyze the problem, it says there that it will enhance. Okay, enhance, meaning that it will be enhanced using the module. So if you will enhance that, that means that your average grade will be greater than 75. So that will be the alternative hypothesis. Now, looking at the alternative hypothesis, what is the direction? Is that directional or non-directional? It is Greater than, so it is directional right-tailed. Why directional right-tailed? Because if you're going to do the normal curve, this is the mean, this is the area, so it is right-tailed because it's on the right side. Okay, next. Another example, an electric company says that the average consumption of residents in a certain town is 300 kilowatts per hour every month, but the town's mayor says that the residents consume less. So what will be our null hypothesis? Our null hypothesis is that the average electric consumption of residents is equal to 300 kilowatts per hour. And the alternative hypothesis is the average electric consumption of the residents is less than 300 kilowatts per hour. Because it says there that the mayor says it's less than, right? So if you are going to translate the null hypothesis into mathematical form, we could write that the mu is equal to 300 kWh or kilowatt per hour. But if we get the HA, that will be mu is lesser than 300 kilowatt hour. So now, by this null alternative hypothesis, rather, what is the direction of the graph? It is directional left-tailed. Very good. Now next. Oh, okay. Because of the null hypothesis, there are also times that because of the hypothesis testing, there are types of errors that we could commit. Okay, again, there are types of error that we could commit. There are two types actually. Okay, now we have the types of error. Because of the hypothesis, so sometimes your hypothesis, you might be able to commit a mistake, and that is what we call types of error. So we have two types of error. We have type 1 error and type 2 error. For the type 1 error, the null hypothesis is true, but you reject the null hypothesis. Example. Okay. So let's say, for example, we have Peter. Peter was a suspect of a murder crime. Okay, but actually, in reality, Peter is innocent. Okay, so during the trial, Peter have submitted pieces of evidence that is saying that he is an innocent, and that is true. That is the null hypothesis. But the judge still rejected the null hypothesis and said that you are guilty of murder. So the judge committed a type 1 error. Okay, now for the type 2 error, so we have the null hypothesis is false, but still you accept the null hypothesis. Another example, so let's say, for example, we have Pedro. Pedro is the suspect for the murder crime, and Pedro actually did it. In reality, he did it. He is a murderer. Okay, but he have given pieces of evidence, but those are not true evidence actually. So, but still, during the decision, the judge accepted the null hypothesis that he said he is innocent, that Pedro is innocent, but in reality, he is actually a murderer. So the judge committed a type 2 error. Okay, so that is type 2 error. Okay. Okay, still part of your module 7 is conducting the hypothesis testing with test on single population mean. Okay, so how do we do this? So let's first review the confidence level and level of significance, of course. So we have 95% confidence level, 5% confidence level. So if you're going to do the normal curve of the 95% confidence level, it's like this. So if you're going to look at it, the alpha sub 2 is equal to 0.025. So ito yun. Okay. The Z score for 95% or 5% significant level is negative 1.96 and positive 1.96. So this is the upper confidence limit and the lower confidence limit. Okay, so the area here is 0.025 and 0.025. Okay, so next. So here, so we have here the commonly used confidence level. We have for the Z score, we have alpha, one-tailed, or two-tailed. So it's very important also that you know if your if your alternative hypothesis is directional or non-directional. So these are the commonly used. We have one-tailed for 10% significance level, or if it's 10% significant level, then that means that it is 90% confidence level. 95 confidence level, 98 confidence level, and 99 confidence level. So one-tailed, two-tailed. Again, it's very important that you should know your alternative hypothesis if it's non-directional or directional. Okay, we have a rule here. If n, or the sample size, is greater than or equal to 30, the sample is sufficiently large. If n is lesser than 30, the sample is said to be small. Anong gamit nun? What is the use of that? Case 1. If the population standard deviation is known or the sample size is greater than or equal to 30, then use z-test by this one, right? We used this already. This is just a review of your previous lesson. If the population standard deviation is unknown and the sample size is less than 30, then use t-test. Okay, this is also our previous lesson. So that is module 5 and 6. Okay, so to summarize again. Okay, if population standard deviation is known, n is greater than or equal to 30, z-test. N is lesser than 30, z-test. Standard deviation is unknown, n is greater than 30, but sample standard deviation is given, so you could use z-test, and n is lesser than 30, t-test. Alright, so now let's have an example of what we have discussed a while ago. So example, a study claims that all senior high school students in the University of the Cordilleras spend an average of 8 hours in studying lessons during weekend. A researcher wanted to check if this claim is true. A random sample of 45 students showed that they spent an average of 7.68 hours studying. The population of such time spent in studying is normally distributed with a population standard deviation of 2.1. Use 5% level of significance. Okay. Now, let's first identify the given. Okay. Our population mean is 8. Our sample standard deviation is, sample mean is 7.68. Our population standard deviation is 2.1, and our sample size is 45. Level of significance is alpha is equal to 0.05. What is our step 1? Step 1 is you have to construct or make your null hypothesis and alternative hypothesis. Our null hypothesis is that the claim, right? It was the claim. The average time spent by students studying during the weekend is 8 hours. So mu is equal to 8. And what is the alternative hypothesis? The alternative hypothesis is the average time spent by students studying during the weekend is not 8 hours. So that is your step 1. Step 2. But before we go to step 2, we have to analyze first the problem. The parameter given there is the population mean. That is the data from the population, right? And what type of alternative test are we going to do? It is two-tailed, because going back to our alternative hypothesis a while ago, isn't it that our alternative hypothesis is mu is not equal to 8. That is our alternative hypothesis. And because of the symbol not equal to, and because basing it from the problem, it's not equal to, then we will have two-tailed test. Okay? So two-tailed test. And let's identify what are we going to use. Of course, we are going to use ZY because population standard deviation is known and n is greater than or equal to 30. What is our n again? It is 45. Now, step 2. Let's identify the tabular value that we are going to use. It's 5% level of significance and it's two-tailed. So meaning we will get positive negative 1.96 or the absolute value of z is equal to 1.96. That is our step 2. Okay, if you're going to draw your normal curve, it's like this. So it's like that. So we have here, this is the normal curve. So that you could imagine. This is negative 1.96. This is positive 1.96, right? So, okay, let's shade it. Alright, that is the acceptance region. Okay. Alright, so now let's solve. That is our step 3. Okay. We have here, if you could notice, we have tabular value and computed value. The tabular value is what we got from the table a while ago. The computed value is z sub c is equal to the sample mean minus the population mean quantity times the quantity square root of n all over sigma. Okay. Now, you might be confused. On your module, the formula for z computed value is equal to x bar minus mu quantity all over square root of n is sigma. That is what is on your module. So this one is the same as this. If you are going to simplify this, it's the same as this. Okay? So let's now solve. So our sample mean is 7.68. Our population mean is 8. So 7.68 minus 8 times the quantity square root of 45 all over 2.1, which is, your 2.1 is the population standard deviation. So the answer is z computed value is equal to negative 1.02. Let's go back. Negative 1.96, positive 1.96. What we have solved is negative 1.02. So negative 1.02. Okay, let's see. Let's go to the next step. Okay, hold on. Okay, all right. So just to reiterate to you, again, this is the normal curve. Let's say this is the normal curve. Inside is the unshaded part is the acceptance region. So later on, what is acceptance region? We will see later. Okay, so our tabular value is 1.96. This is negative 1.96, but we got a computed value, C computed value as 1.62. So look at that. Where is 1.02 located? Acceptance or rejection region? Okay, let's see. So since the computed value 1.02 is less than the tabular value, which is 1.96, accept HO. So, meaning, our conclusion, there is enough evidence to affirm that the average time spent by students in studying during weekend is 8 hours. Okay? Again, in only the level of significance 0.05. That might be different on the other significant levels like 0.10, 0.5, like that. Right? So, that is our example number 1. Let's have example number 2. We have a psychologist asserts that the mean age at which children start walking is 12.5 months. Dr. Bantasan took a sample of 18 children and found that the mean age at which these children start walking was 12.9 months with a standard deviation of 0.8 months. At 99% confidence level, is there enough evidence to claim that the mean age at which children start walking is higher than 12.5 months? Okay. Look at that, huh? So, first, a psychologist asserts that the mean age at which children start walking is 12.5. But the claim that the claim is the mean age of which children start walking is higher than 12.5 months. Okay, let's construct. Okay, identify our given. Our sample population mean is 12.5. Our sample mean is 12.9. Our sample standard deviation is 0.8. The n, or the sample size, is 18, and the level of significance is 0.01. So step 1, let's construct our null and alternative hypothesis. The mean age at which children start to walk is 12.5 months. Mu is equal to 12.5. And the alternative hypothesis, the mean age at which children start to walk is higher than 12.5 months. That is now our alternative hypothesis. Okay, next. Alright, so let's identify, or let's check our given. So up here, that the population mean is given, and of course the type of alternative hypothesis test is one-tailed test, because our alternative hypothesis is greater. We use greater. Okay, so going back to this table, what are we going to use? Is n greater than 30? No, n is lesser than 30, and you do not know the population standard deviation. So again, ulitin ko, if you are going to check the given, we have it, the n, or sample size, is lesser than 30, and population standard deviation is unknown. So what is given is the sample standard deviation. So we use the t-test. Okay, next. Going back, I have given you already this t-value. We could use that if you want. Okay, so step 2. Alright. So step 2, let's draw it, and then let's identify. When we draw it, this is your normal curve, right? So how do you identify the t value that we are going to use? The significant level is 0.01, df is 17. So let's go back to the table. 0.01, one-tailed. We use one-tailed. And then 17. So we can use 2.567. Let's check. It's 2.567. So that is your t value that we are going to use. Okay, that's step 2. Let's now solve. So same formula. We just have to change the square root, the population standard deviation to sample standard deviation. So if you are going to answer that, the answer is t computed value is 2.12. Again, our computed value is 2.12. Our tabular value, which we have seen in the table, is 2.567. That is step 3. Next. Okay, so if you are going to draw it, it's like this. So our tabular value is 2.567. Our computed value is 2.12. So is it in the accept or reject region? Okay, step 4, since the computed value 2.12 is less than the tabular value, t is equal to 2.567, then accept HO. Step 5, there's enough evidence to affirm that the mean age at which children start to walk is 12.5 months. Okay, so that is our example number 1 and 2, and that is our lesson for Module 7.